Hello, I welcome you all. The problem reads a 10 kg cylinder D, which is attached to a small pulley B, is placed on the cord as shown. Determine the largest angle theta so that the cord does not slip over the peg at C. The cylinder at E also has a mass of 10 kg and the coefficient of static friction between the cord and the peg is mu s equal to 0.1. This problem is coming from the Engineering Mechanics Statics textbook 13th edition by R.C. Hibbeler. We have been asked to determine the largest angle theta, okay, so that the cord does not slip over the peg at C. And we've been given the mass of D, cylinder D and cylinder E. Both they weigh or they have got a mass of 10 kg. And when you look at the behavior at C, you can either have the cord moving this side, tendency to move the other side like so. It can have the tendency to move, I've shown in the arrow in black, or it can have a tendency to move like so, like I've shown in the arrow in red. So we are going to test two sides to check which one is going to give us a minimum angle. I mean the maximum angle. But we do know, one thing we do know is when the tension is high in this cable BC, when we have the tension higher on this side, the angle tends to reduce, right? That we know, right? Because this is a continuous cable, right? Of course, there's going to be friction between the peg and the cable. But as the tension increases in BC, you expect the angle to reduce. So we are referring to the tension increasing relative to the tension in cable CE. The tension in cable CE won't change, it will be the same, right? Due to this mass 10 kg. But the only tension that will be changing is tension BC. And as this tension changes, if it increases relative to the tension in cable CE, then we expect the angle to reduce. And as the tension reduces relative to the tension in CE, we expect the angle to increase. So we already know which direction to take. But for the sake of everyone, I'm going to do both of them. I'll check both of them even when I know which side is going to give me, which case is going to give me the larger angle. All right. So what I've done is, or what we're going to do is to draw the free body diagram. So I've done the sectioning. I've sectioned here, I've sectioned there. All right. And then I've got now two free body diagrams. So we're going to draw the free body diagrams, apply the equations of equilibrium, and then begin to solve. So let's go to the next page. Here we are. So let's now add some meat to this skeleton. So let's say we have tension there. Of course, we are going to have tension, and we call these cables as having tension TB, TB. We expect to have the same tension in this because this is a continuous cable that is going over the pulley and there is no friction over this pulley. So we expect the same tension throughout. And it will have the same angle. These angles is already given, which you've seen here. They already gave us these angles, right? They will have the same angle because this cable will tend to realign itself so that it has the same angles and the same tension throughout. So we have this here, this angle there, theta, and also this side theta. Okay, and we have also here the same tension TB, and there we are going to have what I'm calling tension E. Okay, and there I'm having my tension D, which is just equal to 10 times 9.81, which is just basically equal to 98.1 newtons. And so is this one here. I will have 10 times 9.81, which is just basically equal to 98.1 newtons. All right. So I have the free body diagram A and free body diagram B. Of course, I will start with the free body diagram A, apply the equations of equilibrium. So we know that summation of forces in the y equal to 0. What we have we have these are the tensions are the same, so this is just 2 TB sine theta, okay, minus 98.1 equal to 0. Therefore the TB is just going to be equal to dividing 2 into 98 there. This just gives us a 49.05 divided by sine theta. Right. So we are done with this first case. This one has consumed a lot of space. Alright, it's fine. So let's create a boundary here. Okay, there we go. So what we are going to do now is apply the equation that we've always been using in the previous case. This equation is as follows. So let's first call this case as case 1. Like I said, we're going to have two cases. So in this particular case, let's assume that TB is the one that is larger than TE. Okay, and if this is the case, it will tend to pull on TE. Okay, so if this is the case, then we expect TB to be equal to T2 and TE to be equal to T1. In the model, T2 is equal to T1 e to the power mu beta. T2 is always greater than T1. Okay, so what else do we have? Let's check on the mu. The mu has been given as 0.1. Therefore, mu is equal to mu s is given, which is equal to 0.1. Okay, what about beta? Beta we do not know. The beta here, if you look at this, if we are to draw this, we have a cable going straight down like this. Okay, like this. This is TE, and then we have another cable which goes somewhere at an angle like this, which is TB. So we have this angle here, which is theta. Okay, so we have 90 plus theta. So this one there is theta. This one here is theta. So it's 90 plus theta, right? So our beta is equal to theta plus 90 degrees. Converting it to radians, beta will be equal to 2 pi times theta plus 90 degrees divided by 360 degrees. Alright, I think we have all the information and we are still on case 1. Don't forget we are on case 1. This is the case we are dealing with, right? So let's start doing the work. So case 1, let's replace these values. So we said TB is equal to T2, therefore we'll have a 49. We have a 49.05 divided by sine theta equal to, and T1 is a TE. What is our TE? TE is 98.1 to the power, times e to the power mu. Mu is known, times beta. I will not write beta in there because it's too big. I'll replace it later on. Okay, rearranging this and leaning on both sides, we are going to have an expression like this. Lean, we have rearranged and we want to lean both sides. So we're going to have an expression ln 98.1 comes under there, 49 divided by that and everything. Okay, let me just write what we're going to have. So we have an expression like this, 49.05 divided by 98.1 sine theta, okay, which is equal to ln E times ln E times 0.1 beta. Okay, and if we were to simplify this further, this just becomes ln 0.5 divided by 0.5 divided by sine theta minus zero point 0.1 by beta. Beta you said is 2 pi theta plus 90. So let's bring back beta there. So this becomes 0.1 times 2 pi theta plus 90 divided by 360 equal to 0. Okay. So with that, we therefore have something like this if we are to further simplify it. So minus 0.2 pi theta plus 90, just minus, let me go underneath, 0.2 pi theta plus 90 divided by 360 equal to 0. Okay, so once we've reached this stage, we're now going to use what is called the trial and error method. Okay, so I'm using a number line, there are 0, plus, minus, and plus. So I'm trying to move closer to 0. So I want to write this as a function of theta. So writing this, it will be the function of theta is equal to ln 0.5 divided by sine theta minus 0.2 pi 9 theta plus 90 divided by 360 equal to 0. Okay, so this is basically what I'm doing right now using the trial and error method, which I've used before in my previous videos, and this is a known method. Alright, so there we go. I'm going to draw something like this here, and then I'll try out some value. I have theta and the function of theta like so. So I'll be plugging them in there and then looking at the value. The idea is on the number line, on this number line here, basically what we are doing is we have 0 as our center, negative on the left, negative, positive on the right. So we want to find some values as we try out the values of theta, okay, in this function. We want to find a number, okay, or a result from the function that will have a negative, and then the other number should have a positive. We need to find theta that gives us a number positive, other theta that gives us a number negative. And once we have a negative and a positive value, it means the solution is in between. Then we keep on taking averages, and doing the iterations, right? So you can start with any angle you want with. For me, I'm going to start with 10. So 10 degrees. If I plug 10 degrees in there, I plug 10 degrees, I'm going to have a 0.8. Okay, I plug 30 degrees, I'm going to have minus 0.2. So the two values we've seen, 0.8 and minus 0.2, it means the solution is in between 10 degrees and 30 degrees. So I'll take the average of the two. The average of the two is 20. Then I'll plug 20 back in the function and then get the result of 0.18. Again, I'll pick the average of 30 and 20 again, because it is again. So we keep on doing the iteration as we gets as we get closer to zero. That's the idea. Okay, we want the results to converge. So again, the average of 30 and 20 is 25 degrees. We do that, we have a minus 0.03. Okay, we keep on doing that. Okay, we have a 22.5 degrees, we have a 0.07. We keep on doing that. So this is the margin of error that we are getting on the right. We keep on doing that. 23.75, we have 0.02. Okay, I've run out of space. Okay, I think I'll just do it just here. I'll continue here. All right, so I continue here. There we go. I continue. So from 23.75, I have a 0.02. I'll continue from 23. I'll have a 24. So these are all averages, right? 24.375. I will have a minus 0.007. This is good. I can end here if I wanted to. The error is small. Okay, I'll go ahead. I want an error maybe of 0.001, 24.06. I'll have an error of positive 0.005. I'll continue till I reach a 24.22. I'll have an error of minus 0.001. Okay, this is good enough for me. So I'll therefore say, my average or my approximate angle there is going to be equal to 24.2 degrees. This is for case 1. Okay, mind you, we are just on case 1. Okay, this is on case 1 where we assumed that TB was greater than TE. Okay, this was case 1. Okay, so we move on to case 2. Case 2, we are going to assume that TB is less than TE. Okay, so if that is the case, then we expect TB to be equal to T1 and TE to be equal to T2. So writing this, we are going to have 98.1 is equal to 49.05 sine theta times e to the power mu beta. Mu and beta, nothing changes. We replace all the other values and simplify that. This is going to give us ln, we ln both sides. We'll have ln sine theta. We'll have ln sine theta minus 0.2 pi times theta plus 90 degrees divided by 360 equal to 0. So this as a function again, as a function of theta, like that. As a function of theta, like that. In the previous case, we used the same trial and error. So let's draw our table. Something like that. Okay. Okay, let's draw a table. We use trial and error again. Okay, so we have theta there, we have function of theta like so. So we start again doing those iterations. We start again, let me use red. So I'll start with 10 degrees again. I'll have a minus 1.23. I move on to 30 degrees. I'll have 30 degrees. I'll have minus 0.21. Then I move to 45. I'll have 0.11. So I realize my solution is in between 30 and 45. I can get an average of this. Average of that gives me a 37.5, right? Average of that gives me a 37.5. I plug it in the function, it gives me a minus 0.02. I get the average again of the two. Once I do so, then I'll have a 41.25. I do that, I'll have a 0 point, plug it in the function 0.4. So I'll continue in that manner. 39.375. I'll have 0.01. I continue like so. 38.438. I'll have a minus 0.006, minus 0.006. I continue the iteration. 38.9. I'll have a 0.003, 38.677. I'll have a minus 0.002, and finally 38.79. I'll have 0.001. Okay, I'll end here. Therefore, my theta here, my theta there, my approximate theta that I've found at least is equal to 38.8 degrees. This is for the second case. This is for the second case, and this case was TB assumed is less than TE. So when you look at the two, you realize that theta minimum that you can have there is a 24.2 degrees, and the theta maximum, that is what they asked us to find, is a about 38.8 degrees. Let me check the question. That was about it, right? Determine the largest angle that the chord does not slip over the peg. So we found the maximum, but we've also found the minimum. Okay, so this is the final solution. This is the final solution, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing, sharing my channel, give me a thumbs up. Bye bye, and see you in my next screencast.